take a minute or so. Let's take a look at these. Thank you for wearing a mask today. I appreciate that. Okay, let's go ahead and take a look. This is from last semester or the semester before that, depending on when you took this, so should know this, right? Yes, I'm being facetious. So, right, what's happening here is that we're going to have hydronium. So if you put water and acid, what do you get? You get hydronium. Hydronium is the electrophile, right? We know that this pi bond is our nucleophile. We know that water is a good leaving group. Right, so therefore we can say nucleophile attacks electrophile, leaving group leaves. All right, that will get me to, let's put it up here. That will get me to this state. All right, so I got the hydrogen and I form a carbocation. Then my water now has a lone pair. That makes a good nucleophile. So if we do our labeling, right, here's my nucleophile now. Here's my electrophile. Positive charges are often are easy to find, right? So nucleophile attacks electrophile. Let's pick the right color. Now we get our hydrogen, our OH, right? That's protonated, right? And we don't want to leave it in that form. So what we'll do is bring in water, right? And that will do a proton abstraction. All right, so we can think about this acid base, proton abstraction, or proton transfer is what the book likes to use, and I like that term too. Okay, and we get our product. So we end up with an alcohol. For those who haven't had my class before, if you are a verbal learner, and many people in universities tend to be verbal learners, in higher education, in all education, we favor verbal learning over every other form of mental skill. And so therefore, y'all tend to be verbal learners. So if you're a verbal learner and not graphical like I am, then what you want to do here is you want to turn it into a sentence, right? Alkenes reacting with water and acid create alcohols. That's how you're going to learn this, right? By just staring at the picture, if you're not a graphical learner, you're going to have a harder time. But you can translate everything we do into a process sentence, right? And then what you can say it out loud, learn it that way. Okay. The second one, okay, I've got sodium and I've got an epoxide, right? So here's an epoxide. And over here, I've got a thiol or a thiolate, right? Because it's got a negative charge on. How do I know it has a negative charge? Because I know that sodium, lithium, and potassium are positive, right? That's the way they're stable. They want to lose that electron to become stable. So whatever is next to them is always going to be negative, right? So therefore my sulfur is negative. That makes that a good nucleophile, right? So again, identifying things as nucleophile electrophiles. If you didn't learn how to do that this year, please do. Then over here, what I have is I have two electrophilic positions. I've got an electrophilic position there, and I have an electrophilic position here. Is there a difference between these two electrophilic positions? Yes, this one is sterically hindered, right? And this one is not. So then the question becomes, is this something that would attack, or is this something I'd have to make attack? So the question on this one is that thioate, right? Is it a good nucleophile? So sulfur nucleophiles. Sulfur nucleophiles in general are good nucleophiles. And what about negative things? Do negative things want to give away their electrons? Hell yes, right? So therefore, they're going to be better nucleophiles than non-charged species. So in that case, right? I know that since this wants to react, I don't have to protonate that epoxide. It's going to react. And what I have here is a base promoted ring opening, right? And base promoted ring openings favor which side? Oops, didn't mean to do that. They favor the least sterically hindered. So therefore, I'm going to attack the least sterically hindered side, and that is going to give me, oops. That's going to give me my O minus here, which I can put next to my potassium, my sodium, and my thiol. Now it's a thiol. Okay. Questions about these two reactions? Again, if you think about this as a process, it's going to be easier for you to learn the information and recall it. Okay. So when you're going through the review, please do that. Okay. All right. So we've got a couple of things. One is that I did find a online homework system. That's this Chem 101. Okay. This is my view of it. You can get the app. It works on phones. It works on computers, so forth. Let me change it over to your view. This is what your view would look like when you come in. Now, I don't have any assignments for the class because we're not going to use it in class per se. We might play around with it later in the semester, but at the beginning of the semester, this can be a response system, and let's not go anywhere we don't need to go right now. It's hard enough to get to class, wear your mask, and not freak out that you're in organic chemistry again, right? Anybody have nightmares yesterday? You'll get to the point where you'll tell each other and it won't embarrass you, so it's okay. But we got homework, right? So we got 2 homework assignments. The getting started is not for a grade. The second one is for a grade, right? So the first one, the organic review, is for a grade. I'm giving you an extended amount of time for this. Usually I'm going to give you about a week to do these so that you can stay on track. This one I've given you a long time because I want you to get comfortable in the system. This has a 2-week preview that started yesterday, sadly, but 2-week preview that you can get on here, register, form account, and you don't have to pay for 2 weeks. Okay. It is $28 for the semester. If it's between this and a textbook, get this. This is going to be part of your grade. You can use any textbook. You can use your grandmother's free organic textbook, and it'll probably get you 95% of the way there. Okay. So this is the whole online homework system we have. As we go into it, you'll see the different types of problems we have. You know, if I just pick one of these, it's multiple choice. Some others, let me see if I can find one. You know, it's got a drawing system here, so I need to draw this. So I click on here, and I'm going to draw the product of this. So I'm going to start over here and go boom, boom, boom. And you don't have to make the sounds. That's not necessary. It'll work without making the verbal sounds, right? And so I do that, and then I know that this is, and I'm going to make a mistake here, okay? And then I'll say I'm done, okay? And I can submit, and that's not the right answer. I know that's not the right answer because I picked the problem. But let's see. So you know what I forgot about is the fact that this could rearrange. So let's take this off. Oops. Let's undo that, and let's go and change to this one. And now I'm going to change that to an OH because whenever I go through a carbocation, I can have a rearrangement, right? And this is set up for a rearrangement because I have a secondary position next to a quaternary. And so now I remembered that, I'll do that, and I'll submit it, right? And when you're done with the whole thing, and here it checked it for me, right? So I got the right answer, okay? You got multiple attempts on these. On the multiple choice, I'm going to give you 2 attempts. So use the first one, and if you get it wrong, go review. On the drawing ones, I'm going to give you between 4 and 8, depending on how hard I think it is to draw. Okay, you'll either have 4 or 6 or 8. Okay, again, if you miss the first one, go and review and come back and try it. Okay. What I'm going to do is go ahead and set a non-graded and a graded. I had that idea over lunch. So what I'll do for this one is I'll create another one that's not graded so you can practice. And then I'll do that for each one so that you have more homework, right? More practice is better. And what will be non-graded, play around with that one, and then go do the graded one, and I'll mark it as graded, right? So the first one will be practice, second one will be graded for you. But this is nice because it can tell you if you got the answer right then, you don't have to worry about waiting for feedback. So this is a easy to use tool. I'm very excited that it is mobile friendly. You could do this on the ride in the bus up to campus, right? You can do this at the bar when you're bored. So, you know, that's a good way to, you know, meet people, be working on your organic chemistry. The other thing to let you know is, okay, we didn't go through the Canvas site, but just to let you know how I'm structuring this. So the syllabus is up at the top. The Zoom links, so here are my Zoom links. If you go on one of these, it will open up and it will give you the Zoom link, plus you have the calendar that you can use. So if you click on that, it'll add it to your calendar, right? Consider doing that. If we go back, you'll also see Poppy has some office hours. So she'll have office hours Monday, 3 to 5. Those are going to be in the Stevenson Life Science Research Building, either 3020 or 3440. Okay. And then Tuesday over here in Physical Sciences, 434. Okay. So upstairs, right after class on Tuesday, Thursday. There's her email if you have any questions. When you email me for something, copy her. So if I am dealing with something on campus, and she can get to the question first, she can answer it for you, and then you're good, right? So copy her on everything you send to me, and that way we got two people that can respond quickly to get you the answer the fastest. Okay. If you ever get lost, go back to the home page. Okay, online homework. Here's where you can see the online homework. You know, I've given you the information, the course code, the cost. You can purchase this directly through the Chem 101 site. If you need to use the bookstore, you can also get it through the bookstore. So if you're financial aid, if you're getting reimbursements through the VA, or through a tribe, and they pay for your course materials, you can get this through the bookstore. There may be a surcharge through the bookstore. There usually is a surcharge. It's $28 from the website. And there is 2 weeks. So if you don't know if you want to stay in this class yet, use the free one. You know, don't pay for it until you're sure you want to stay in this section versus switching to another section. But you do have some time to decide on that. Assignments will be listed on Canvas. The assignments will be worth 5 points. I will accept late penalties, but there is late assignments, but there will be a penalty. So if you miss one, you don't have to freak out and send me an email. It'll accept it. Go in, do the online homework late. There'll be a 5% reduction for the first week, 10% reduction for the next week, so forth, so on. So, you know, like I said, staying up on stuff is going to be the way that you do well in here. Okay. So other things, you can also see here that I put in. So you've got the learning outcomes from Organic 1, right? If you want to go through those are all listed right here. Right. And then what you'll see every time we go through a new section, I've got the learning outcomes for this section listed there. This is what you should know. Right under that, I'll put any assignments, right? So once we have a quiz, if it's related to this, it'll be in there. Exams, once we get to exams, they'll be listed there so you know where they are. And also recordings of the lectures. I'll put the URL for the recording of the lectures there. So in case you want to watch them again, okay? So just covering a little bit more of how the class will work. And now let's get to new material. Any questions about Chem 101 or the Canvas site? Yes, ma'am. No, the attempts don't give you, won't be any reduction, but if you do turn it in late, there is. So you won't get a reduction after the first attempt, any of the attempts, but the number of attempts is based on whether it's multiple choice drawing or really difficult drawing, right? So if it's multiple steps, you'll have more attempts on those because you can make errors in the drawing and need to be able to go out, but there's no penalties on it. But I would suggest after you miss it once, go review. Don't sit there and eat up all of your attempts. Okay. Okay. Any other questions? All right. Okay, let's look at the new material then. Let's get started. So conjugated pi systems. So again, just let's go through a little bit of review. The thing to remember with these is that, you know, we can draw it in several different ways. You know, we've got this. We really want to draw all of our orbitals. And if I move on before you finish drawing this, it's going to be, I'll start posting these PDFs as well. Oops, that's not correct. So a carbon out here, right? And then we have so we got this pi system, right? But in this case, I've got pi electrons here, right? But over here, it's all sigma. I can have hyperconjugation. Okay. Remember that term for carbocations, right? I can have hyperconjugation when I have a pi whenever we have a carbocation, right? And we get back donation from an sp3 to the p. So that's why a more substituted carbocation is more stable, because you're getting hyperconjugation. You're getting back donation from the sp3 orbital to that empty orbital, right? But except for this example, we do not have conjugation, right, where there are electrons. We have hyperconjugation when we have a carbocation. And that's the reason for the stability of carbocations. What we're going to be looking at is not single isolated double bond species, but conjugated double bond species, right? So where we have two double bonds next to each other. And that's in contrast to isolated double bonds. And you'll see in your learning outcomes, you should be able to identify these. So if we look at conjugated, what we end up in conjugated is a continuous p orbital path, right? Where over here, what we're ending up with is we've got a p orbital, but then in the middle, we've got an sp3. So this sp3 carbon, right, breaks up that conjugation. There's no conjugation. But here, I could say that I have conjugation through all that pi system, assuming that the pi system is aligned, right? So if we think about it, the pi system has to all be up. What happens if I turn one of these atoms, right? If I start to turn the atom, are they going to be in communication anymore? No, right? So one of the things that we'll be talking about over the next couple of weeks is the fact that whenever you have conjugated pi systems, they're going to favor conformations where we have all of the p orbitals lined up. Okay, so in this molecule, what that means is that this wants to be planar, right? We're not going to have, let me see, some of you are staring at me funny. So let me show you something. So what we have is we have this, right? We're not going to have that, right? So we're going to have the two double bonds like this. We're not going to have one of the double bonds hanging out at you, right? What they want to do is they want to be planar. If they're planar, the p orbitals are all in communication. That's a favored state. If all of a sudden it rotates, right, that's going to be out of line, right? So if we think about it, p orbitals here lined up. Here, no, right? So all of a sudden that's a higher energy state. What about here? Are they lined up? Yes. What would be the problem between this one and that one? This one makes you look like Robot Man. This one makes you look like, no, what? This one is what? More spiritually hindered than that one. But as far as being planar, they're both planar, right? So that can communicate. So this one and this one are viable as far as our alignment of our p orbit. This is not, right? And that is not, right? And after you get a certain age, it hurts to do that. So don't do it too often. Okay, questions about that? All right, we'll get into a lot more about these orbital structures later in the lecture. So how do we prepare these? Well, we can do an elimination, right? And what we want for our elimination is we want a good base. Why would I pick T-butoxide versus, let's say, methoxide with a methyl? What's the competing reaction with eliminations? Substitution, right? An SN2 and an E2 could be in competition with each other. An SN1 and an E1 can be in combination with each other, right? So when we look at this one, we look at the mechanism, we've got our hydrogen, we've got the oxygen, the T-butyl group is just this group, right? Big bulky base. The big bulky base is going to extract a proton. Extracting that proton will be an E2 type elimination, which will result in the diene. Right, and the E2 mechanism is from organic 1. We could also start with an alkene. Again, we would get elimination. Should be antiparaplanar. I didn't draw it that way. And then we just have another one. So we get consecutive E2 reactions to give us the diene. Because the added stability of a conjugated diene system, because of this communication in the p orbitals, if you have a choice between making an isolated and a conjugated system, right, you're going to make the conjugated. So if you're looking at two potential protons to eliminate, and one of them will give you the conjugated diene and the other one will give you the non-conjugated diene, you're going to go towards the conjugated. You might also ask, why didn't this give me a triple bond? Why couldn't I have eliminated to the middle to give the triple bond? You wouldn't be able to do that with this base. You would have had to have an amide base, right? And then it would have potentially been possible, but only with a much stronger base. If this had eliminated to the middle, you would actually see this rearrange before it would get you this product. But we won't worry about that. We're going to take the straight mechanism for this. If you want to look at the energy of that and have a deep discussion about the difference between where this goes, this makes most sense with this base. Okay. Questions about preparing conjugated dienes? Straightforward so far. Everybody remember these mechanisms? Yes, Dr. Morvan, remember E2? All makes sense. Starting to come back. Okay. The other thing we want to look at in this is conformations. So you saw my little conformation dance I just did. What we're looking at, right, is the possibility of having those double bonds down are both double or them one up and one down, right? And again, this is planar. So we got to think about the fact I'm not drawing wedges and dashes. These are planar. This one where both double bonds are facing the same direction is S-cis. That's the nomenclature for it, S-cis. Over here, this one is S-trans. Now, if we look at our energy, the S-cis is a higher energy than our S-trans. And there's, for this specific one, there's about 12 kilojoules of difference between these two states. So they will flip back and forth. And 12 kilojoules, it needs to be a relatively decent temperature, but it's not anything extreme. Rotation of a methyl around a methyl is about 3.6 kilojoules, right? So we're not talking about a bunch. This would be about kind of like a isopropyl group rotating, right? So this is going to be able to go back and forth. And that'll be important when we get to some of our reactions here. But you should be able to identify cis and S-cis and S-trans. Okay. All right. Before you get glassy-eyed, let's do a try this. Okay. Two questions. Is it conjugated or isolated? And then if it is conjugated, tell me if it is cis-trans or S-trans or S-cis. Okay. Not a long time to do that, but let's go through it. This one is pretty straightforward. Okay, the first one here, all right, we've got a double bond, single bond, double bond. Is that conjugated? Yes, that's conjugated. Since it's conjugated, we should be able to determine whether it's S-cis or S-trans. This one is S-cis. And what's also important, this is going to foreshadowing something we'll need later. What's also important, could this one ever be S-trans conformation? Not with the six-membered ring, right? So this one is locked into this structure, right? There's no way for me to rotate that ring and take it into S-trans. So it's always going to be S-cis. The next one, is this going to be isolated or conjugated? Okay. I've got an sp3 carbon in the middle of those two, right? That's going to break up any conjugation between the two double bonds. So this one is isolated. Okay. This next one, isolated or conjugated? It's conjugated. Right? So if we look at it, I've got conjugation here. Does it matter that I have all these other sp3 carbons? No, that's not breaking up this, right? So this is conjugated. I can start at this side of the double bond and go through the other double bond without going through an sp3 carbon. So that's going to be conjugated. Is this S-cis or S-trans? S-trans. And as an S-trans, is this one locked or can it rotate? This one's locked. Okay. So this one is locked because of the ring system. Next one, isolated or conjugated? Okay. This one's got isolation both sides now. I'd have to check both sides, right? But it's got sp3 carbons in both, so this is isolated. Okay. And then this last one, conjugated or isolated? It's conjugated. Right? And then as I've drawn it, what is it? It is S-cis. Could it be S-trans? Yes, it could be S-trans if I had rotated that and drawn it in this form. Okay, questions about these? You want about 100 of these on the first exam? All right, so let's move into molecular orbital theory. We're going to be looking at a new type of reaction in this chapter. We've looked at ionic, we've looked at radical. We're going to be looking at something called paracyclic, and we'll talk about that more. But for paracyclic reactions, we need to go back and delve back into molecular orbital theory, right? And so molecular orbital theory is when we took atomic orbitals and we mixed those atomic orbitals to get molecular orbitals, right? So when we think about ionic molecules like sodium and chlorine, it is a sodium plus and a chlorine negative. One took the electron, the other one gave up the electron, but their structures, their atomic structures, have not modified. When we get to covalently bound molecules, right, like organic molecules, the carbons and the hydrogens and the oxygens are all sharing electrons. Because they're sharing electrons, their atomic orbitals had to modify to become molecular orbitals. That's where we go from S and P to sp3, sp2, so forth, so on, right? All those hybridizations that we learned, that's molecular orbital theory, okay? Where we're going to take it now is we're going to look at pi system molecular orbitals, right? So you're taking atoms, you're mixing all their atomic orbitals to get the molecular orbitals, and there's some things that happen that we can look at when we look at pi systems, right? And pi systems are our weakest bond. We talk about that on Tuesday, right? The pi system is where we're going to have most of the reactions. And so when we think about a pi system, right, if I have a p orbital with one electron, and I have a p orbital with one electron, whenever these combine, so if I have two different atoms, when these combine, I'm going to create a bonding orbital that has electrons in it. right? And I'm going to create a anti-bonding orbital. This one we're going to know as pi, right? That's a pi bond, pi orbital. This one is known as a pi star. So for every pi bond I make a pi star. For every sigma bond I make a sigma star. When we're talking about conjugated pi systems, we're not going to worry about the sigma bonds, right? So we're not going to worry about the sigma and the sigma pi's, but we are going to worry about the sigma stars. We are going to worry about the pi's and the pi stars. For a simple system like the alkene, right, the bonding orbital can be shown in phase, and let's use color. So if we look at our p orbitals, what happens with the, and you can shade these, just shade one dark and one not dark, right? These are going to be overlapped, where these, you can think about this as phases, and that's the term you use, right? Phases. In one case, they're in phase. When they're in phase, they can communicate. When they're out of phase, there is a node. Anytime I have a node, there is no communication. So for a simple ethylene, so this simple ethene molecule or ethylene, I have the pi and the pi star. In the pi's case, I have communication between the two p orbitals. In the pi star's case, I have no communication between those two p orbitals. Okay. All right. I saw a hand up. Were you asking a question or stretching? Okay. Yeah. So the bonding is going to be when it can actually interface and share electrons. Anti-bonding is a case where there's something that's going to be not allowing that sharing, right? So this node. And the way to think about it is phases, right? So we think about the electrons, think about they're out of phase. Okay. Yes, ma'am. No. So if we think about resonance, resonance is a static picture of the bonding distribution of electrons. It never talks about the anti-bonding. So far, really, we haven't talked about the anti-bonding orbitals. They're always there, but just like this, right, they're not full. What we've talked all the way to this point has been full electrons, right, or the absence of electrons, but we haven't talked about anti-bonding orbitals. So when you're talking about resonance, that is just multiple pictures of one, in the terms we're using today, bonding picture, right? And what we see is a distribution of electrons across. You'll see in a second. Well, let's get there. We have other questions? No reason to say foreshadow. It's the next thing on the list. Okay. All right. So when we look at these, right, we can think about that. And one way to think about the ethylene is we have this, right? And we just have two carbons. And so we can just, it was called the string theory, and then physics came up with the string theory. And the physics string theory has to do with subatomic particles that can never be proven. So it makes physicists and chemists' minds hurt. This string theory was really easy, which is if I have two atoms that have p orbitals, I can take a string. If I do not cross that between those two p orbitals, this means I have 0 nodes. Right? As I go up and cross that, right, I have now 1 node. If I then draw, and this is really just kind of an aid, right? If I then put p orbitals here, and I look at the string, I can go back in and I can shade it and say, okay, well, that string was on the top side, so I'm going to shade both of those sides. And over here it crossed, so I'm going to shade that one and shade that one. Right? And so since there's a node here, you'll never see yellow, but let's use orange, right? There's no communication. Where over here, there is communication. So if I wanted to look at it, that one looks like this, and this one looks like that. Right? Now, does this diradical species ever actually exist? No. Why? Are there any electrons in the top antibonding orbital? No. And there's not 2 electrons. So again, that is a state that could exist. And it'll be important for what we're going to be looking at in this chapter, right? It's not directly relevant to ionic and covalent bonding, but it is essential to what we're going to be doing with paracyclic reactions. Okay, so that's kind of the string theory. Now let's look at butadiene, right? So we have this, right? That could rotate and be in this conformation. So this is 1,3-butadiene, right? And this is the S trans form. And this is the S cis form. 1,3-butadiene. So for this one, let's do our string theory. And for this, I'm not going to do them side by side. I'm going to do them up and down. And for those of you that download this PDF later, this is going to drive you nuts, but I apologize ahead of time. Okay, and let's start at the bottom. This is, let's say, 0 node, 1 node, 2 nodes, 3 nodes. So if I grab my string, right, and I go my string, there's my string. With 1 node, right, we start on the top and then we'll go to the bottom. With 2 nodes, right, you can think about it kind of like this. When you do the quantum mechanical theory with this, it actually will give you the distribution of the sizes. And then if we go 3 nodes, we're actually drawing it 3 times through the line like this. So then what I'm going to do is I'm going to draw my p orbitals. And I'll use the string as my guide on my shading. So here I can shade all of these. If we look at the second one, right, I'm going to shade these 2 using this, right? I'm going to shade those 2, but then I'm going to drop to the bottom here. And over here, I'm going to shade up, but then I got to go down for the next 2. Then I'm going to go back up. And then here I've got up, down, up, down. So if we think about direct communication, right? Here's our nodes. So we have 1, 2, 3 nodes, start at 0. But let's go back to that picture of our energy levels. And let's think about the fact that we have 4 p orbitals. How many electrons do we have totally in our 4 p orbitals? Well, we have 4, right? So we have an electron for every p orbital. So when I go to fill in my energy, what do? I have 1 up, 1 down. Now it's full. I got to go to the next molecular orbital. 1 up, 1 down. Do I have anything left to put in the top? No, right? So what we have here is we have our energy gap, right? Now we've gone from our pi's to our pi stars. We've gone from our bonding to our anti-bonding. Our bonding are full, right? Our anti-bonding are empty. In quantum mechanical terminology, this is not 0, 1, 2, 3. This would be psi 1, psi 2, psi, it's not a 4, it's a psi 3, psi 4, psi 4. So I can actually do a quantum mechanical calculation to come up with these distributions of electrons. The string theory was an easy way for chemists who are somewhat averse to doing high-level calculus, and that's the reason we're not P chemists. The string theory was a way for us to do this really quick, right? And we could draw out these pictures. Now, if we think about these pictures, which of these two pictures are the most important to the structure and reactivity of an alkene, of a diene? The top two or the bottom two? Well, which ones have electrons in it? The bottom two, right? So the bottom two. And what happens in the bottom two? What are you seeing? Well, if we look at this psi 1, right? Let me draw it over again, and we'll just use purple. What does this really look like? Well, that's this, right? That's our normal way we show the conjugated diene in our static form. But getting to her question, right? Resonance, what also exists and has electrons in it? This form, which we don't have a really good way to represent, but you could think about it as this, right? That conjugation, right? That we have full communication. So one of the filled orbitals is the field communication. The other one is this kind of double bond, right? But both of these are full, so both of them are part of the character. So this gets back to that resonance structure, right? The molecular orbital gives you a better idea of what's happening in the overall electronics of the molecule. Resonance structures and these two structures here are just difficult ways of trying to show something that's very fluid, right? They're static pictures, okay? The other thing that we need to take away from this before we start to move on is the fact that we have two other terms that we need to think about, and just so we don't really get mixed up, I'll use green here, which is HOMO and LUMO. So HOMO, H-O-M-O, and LUMO, okay? HOMO is highest occupied molecular orbital. LUMO is lowest unoccupied molecular orbital. Okay. So if I was going to move an electron, where would I move it from in this molecule? So let's say I gave this molecule a lot of energy, right? And I got it excited, and one of the electrons was going to jump. Where would the electron jump from? It would jump from my HOMO, the highest occupied molecular orbital, to my LUMO, right? And also, what we'll see when we get to Diels-Alder reactions and the other pericyclic reactions is whenever I have two pi systems react, you're going to have reactions between HOMO orbitals and LUMO orbitals. So when we think about organic one, it was all about heterolytic and homolytic. Here, what we're going to be doing is we're going to be interacting occupied molecular orbitals and unoccupied molecular orbitals. Okay, questions about these? Yes, sir. Sorry, I can't hear you. Let me get away from my computer. Four electrons. those four, right? So I have four in every orbital filled with two, right? So therefore I start and I fill them in and then I run out, right? So there's no more. If it was a radical species, if I gave it an extra electron, it would go into LUMO. What happens if I put one electron into the LUMO? Is it unoccupied anymore? What happens to its name? Now it becomes LUMO, right? They used to play around with SUMO and SOMO, but I'm glad at this level we don't talk about it. SUMO would be if it was singly occupied and singly unoccupied, which makes no logical sense. So don't worry about SOMO. If it is unoccupied, I lose the lowest unoccupied, the LUMO. If I move one electron, and one way to do that, as we'll also kind of see in this chapter, is I can add energy to the system, right? So if I take a ground state species and I hit it with light, let's say, then what I'll get out of that is going to be, and notice I didn't change the spin for this one. I'll end up now, this is my HOMO, right? But this is the excited state. If that excited state doesn't react with anything, what's going to happen to an excited state? It's going to decay back down to a ground state. So one of the things whenever we hit bromine with light to get it to react in a radical reaction, one of the things we were doing was exciting the molecular orbital of the bromine, which then allowed it to split apart into two bromine radicals, right? It had the option of doing that. Most organic molecules are going to decay back down, but there are some molecules that if you excite it, they will form radicals instead of just decaying back down to the ground state. Yes, sir. That's where it gets into the SOMO and the SUMO. Yeah, which just gets confusing. Don't worry about it. So singly occupied molecular orbitals. So a HOMO becomes a SUMO, and singly unoccupied, which makes no logical sense, would be the LUMO becomes a SUMO. It's archaic. It's the kind of thing that you'll pull up at night when you're talking to people over too much wine. So, but it's not going to help you all in this class. All right. Okay, questions about this? All right, let's look at some reactions. So let's step away from molecular orbitals for a second, and let's look at electrophilic additions. So we looked at this, right? We look at the mechanism here. All right, so just an isolated single double bond here. Nucleophile is going to attack the electrophile, leaving group is going to leave. I'm going to form the most stable carbocation, all right, which will be the most substituted carbocation. And then the bromine that's left will come in and attack the carbocation. So this is electrophilic addition to an alkene. When we do that with a diene system, a conjugated system, then what happens here is that I can end up with more than one possible product. Reason for this, right, is that we do the reaction the same way, right? We have our, let's go ahead and label them this time. So we have our electrophilic position, right? We got our leaving group, we got our nucleophile. It's symmetric, so either side could be my nucleophile. Okay, that's going to react with the electrophile. My leaving group is going to leave. And then that's going to create this carbocation. Again, we're adding the carbocation to make the most stable. One thing to consider when I have conjugated systems, which is always going to be the more stable? The one that is in conjugation, right? So not only would I have made a primary if I had reversed these, it would have been an isolated carbocation. I always like carbocation to be conjugated. But since it's conjugated, what can I do with that? Well, I can draw the resonance structure, right? So I can change this through resonance structure, and I would get this carbocation. If I then had the bromine react with this first one, right? Nucleophile attacks electrophile. And I'll end up with the bromine going up, right? Or if the bromine in this other case attacked here, and let's leave the H on for right now, I would get this species. So since I have conjugation, I'm going to have two resonance structures. Those two resonance structures are going to result in two products. Okay. Whenever you're reacting an electrophile with a conjugated system, you always want to create a conjugated carbocation. Okay. So when you create that conjugated carbocation, that means that you're going to be able to rearrange that. So get the resonance structure, that's going to give me my two products. Now, terminology is important here, so let's go through that. If we look at where our hydrogen is attached, let's call that 1. Doesn't matter what the nomenclature is, wherever the hydrogen is attached, that 1. What would I call where the bromine was attached? That'd be the 2, right? So this is a 1-2 addition. Over here, again, where the hydrogen is attached is 1. Where is the bromine? 2, 3, 4, right? So this is a 1-4 addition. So that means up here, I can name my two products. This is the 1-2, they call it adduct. And this is the 1-4 adduct. And I believe I have a picture. Fuzzy picture, but a picture. Okay. So when we look at the energy here, what we see, right, is that we go through the carbocation, right? And then we're going to end up with the two differences. Notice that the 1-4 here is the most stable. It's the lower energy. Why is the 1-4 more stable? Is it the fact that it's a secondary bromide and a primary bromide? That would only have an impact if the nucleophile was coming in to attack it. So by itself, it's not stable, but the primary bromide could be more reactive to a good nucleophile. But that doesn't have anything about the nature of the molecule. What's the other difference you see here? Well, this one has how many substituents? So if we look at that double bond, this is monosubstituted, right? What about this one? It's disubstituted. What do we know about the stability of alkenes? More substituted alkenes, right, are what? More stable. So why did you have to learn that? For this problem right here, okay? So more substitutes. So that's why the 1,4 adduct in this case, right, is going to be the more stable. Now, is the 1,4 adduct always? Not always. The more substituted is going to be more stable. Most often that will be the 1,4 adduct, but not always. You potentially could draw a diene that when you reacted, the 1,4 adduct was not the most substituted product. Okay? So don't fall into the overgeneralization rule. Why is the 1,4 adduct in this case the more stable? Because it is the more substituted, not because it's the 1,4. So if we look at the reaction, right, we can also come up with the products, right? So let's look at thermodynamic. We have time? Yeah. So let's say we do this reaction, and I'm going to do it at 2 different temperatures and look at my products. Okay, I'm going to run it at 0 degrees Celsius, right, in an ice bath. In this case, I get 71% of the 1,2 product, and I get 29% of the 1,4 adduct. Run it again at 40 degrees C. I get 15%, right, and 85%. When we look at the low temperature, right, those are kinetic conditions. Why are they kinetic conditions? Because whatever happens first is what I want. Fast, right? Kinetic. This one is the thermodynamic. I don't care how long it takes. I want the most stable product, right? So kinetic is the fast product. The thermodynamic is the most stable product. And we see here, as we raise our temperature, right, we can see that this is the most stable alkene. So if I give the system enough energy, right, it's going to go back and forth and back and forth. And even though this nucleophilic attack to get to the 1,4 is higher, if I give that enough energy, it will go through this path to get here, right? Because there's a bigger energy gain here than there is an energy gain here. So by giving it enough energy, I can make it go to the 1,4. So the thermodynamic product is always, the thermodynamic product is what? The most stable product. Okay. But then why is the 1,2 the kinetic product? Well, for that one, you got to think about what's happening in the solution. So whenever we have our double bond, right, we got our HBr, and I show it this way, but let's change that a little bit. Let's do it what would happen in solution. So let's put this there, right? This is going to react with that. They have to be in close proximity, right? Electrons aren't going to fly halfway across the galaxy to get there. They got to be in close proximity. Electrons, that needs to be close to the bonding distance for carbon to hydrogen. Could be a little longer, right? But not really far. Needs to be within that kind of range, which means that whenever this comes off, where's that bromine? Well, that bromine is where? Right next to that carbocation. Is that positive carbocation and that negative bromide going to be attracted to each other? Yes. Are they close to each other already? Yes. So if you don't give it enough energy to rearrange, and that bromine have to go find that carbocation, what's going to happen? They're going to react, right? So in the 1,2, it's proximity. There's a proximity factor that makes the 1,2 the kinetic, the fast, right? Where that's not in the place for the 1,4. So the 1,2 has a proximity advantage, which makes it always the kinetic. Remember what I said? The thermodynamic is not always the 1,4. It could be the 1,2. But in the kinetics, because it's based on proximity, what is going to be the kinetic product? In this reaction, not all reactions, in this reaction, the kinetic product is going to be the 1,2. Okay. So if you have low temperature, look for 1,2. If you have high temperature, you're looking for the most stable. Let me say that again. If it's a low temperature kinetic, then your 1,2 is going to be favored, right? Because it's proximity. If it is a higher energy reaction, thermodynamic control, then it's going to be the most stable alkene. Could be 1,4, might be 1,2. You better check. Questions about this one? Okay, let's try a couple of reactions. Okay, on the first one, just give me the product. Second one, give me the major product. In the first one, right, we make the brominium ion, So if it is the 1,2 addict, we should still expect it to have a stereochemical control. So you can see the 1,2 has the anti-addition. The anti-addition doesn't hold as well when we look at the 1,4, right? But since it is a conjugated diene, I do have the possibility of two different products, a 1,2 and a 1,4 addition. On the second one, we could have the bromine here, right? Or we could have the bromine here. In this case, is this more kinetic type conditions or thermodynamic? Low temperature, trying to tell you that this is kinetic, right? So I want to try and do kinetic control. Sometimes you might see -20, sometimes you might see -78.